If you don't, then it's going to bite you in the butt in future classes, dynamics, C204, whatnot. Okay. All right. So let's talk about the quiz real quick. Go ahead. There we go. Okay. All right. So there's the quiz. So, fair number of you got it correct, which is good. If you didn't get it completely correct, it might have been the way you interpreted it. So overall, actually, I don't know if you can you guys see that? Or are you looking at me?
We can see your screen.
We can see it.
Okay, good. Thank you. So what I wanted in this problem was this weight, and how much weight could you put on it so that the maximum moment about E didn't exceed 300 Newton meters. And so when you think about exceeded, that means it exceeds it in either direction, counterclockwise or clockwise. And so when we do these types of calculations, we always look at moments as negative or positive, depending on their orientation. The way you would structure this problem is you would take a moment about E, and you would essentially take a moment about E, and you'd have your 7,500, 200 Newtons. Those would all be going counterclockwise. And then you'd also add in the 300 Newton meters, and then it'd be your weight times this distance equals 0. And so you had two calculations, one where your moment about E, you're setting everything equals 0, but your moment about E is always going to be either 300 or negative 300. So I posted the solution on Canvas. So take a look at it if you're not sure about it. Chances are it's probably a small mistake. So I wasn't doing it to trick you. I just wanted to make you guys think about, now that we're in equilibrium, you want to think about everything that's going on in a system. So there's no more just resultants. Everything sums to 0. The second part was the tension in the pulley. And this one overall, I think you guys did okay. I was hoping more of you would have got it, but it's only worth 5 points. And I know I haven't talked about pulleys. This is more of just an assessment to see if you guys have seen these before. One thing is if you have to take dynamics next quarter or in the future, which a lot of you do, this class, there's a lot of pulley work in there. So it's good to understand how pulleys work and what they do. So on this one, for example, you have the 100 kilograms, and the way you want to look at these is to the left here, you have the 100 kilograms, and then I've expanded that in this picture right here. And when you cut the tension, you have 100 below, but you have 2 cables going up. So each of those cables is going to support 50. And then once you have the 50, that 50 corresponds to this line that's on the center pulley, which I've drawn up here. And so 50 kilograms goes up, and that equates to 25 on each side. And once that 25 is there, it just goes around the pulley and down to the motor. And so the final answer is just 25 times gravity. So I may have a pulley question on the test. It's more conceptual. If you look at the last tests, I did put a pulley on. I think a couple of them were a little more difficult than I should have, given how little you guys have covered it. So I'll probably make it easier if I do put it on there. So I learned something from that one. But again, if I make a mistake on the test and I have a question that's too hard, then I just curve it accordingly. All right. So midterm format. So as of now, I have it so that it's going to be 3 or 4 questions that in an increasing difficulty and value. So usually the first question is say 15 points, and it's meant to be fairly easy and not real challenging. Just something that a basic conceptual question or a basic calculation. And then and so then it'll go on up from there. Now, Similar to the questions will be similar to homework, but in some cases I may only have you do a few steps. And so I know that given the time limits, I'm not going to give you a lot of full on calculations because I know some of these problems take a while to do. And I'm not looking for your algebra ability or your ability to solve three equations and three unknowns. So the exam, the exact time I haven't ferreted or haven't determined yet, but it'll be about 60, 70 minutes, including upload time. It'll be available between 8 and 4 on the day of the test, and it'll be asynchronous format. Hold on, let me get rid of this bird. It's driving me crazy. Hold on just a sec. Sorry. Sorry about that. Perils of working at home. Be nice to be back in the fall. Okay, so as I was saying, time limit is about 60, 70. That'll be finalized. I think that the big difference with this test versus the last two quarters is I decided to give it asynchronous format. If I went with having to take it between 8 and 9 or 9 and 10, as I did last quarter, you would be limited to just 50 minutes. And I think that historically, even if I reduce the length of the time, I think it's very stressful to try to squeeze that in 50 minutes. I mean, that's what we'll have to do when we get back to the real world. But for now, I think given the fact that it's an online course and I don't think it's as easy to learn the material as it would be if we were live, I'm going to change it and give you more time. So that said, you'll be able to pick a time sometime in those 8 hours to do the test. One thing about the asynchronous format is that I won't be there for you to ask questions. I will be available by email most of the day. So if you do have a question, you can ask it. But what I would say is if in the event you can't get hold of me, the best thing to do, and I'll try to make these as clear as possible, but just state your assumption and move forward. That's the best thing. So that way I can look at your assumption, if it's reasonable, even if it's, has to be reasonable, of course, but then that kind of saves you from just making some wild guess on something. And the other thing is be sure to read the problem. So you may have noticed on one last test I gave, I think it was either winter or fall, I gave the option of doing two problems. So you could pick one or the other. And I had people that did both, and then they didn't have time for the last problem, which you don't want to do that. I don't know if I'm going to do an option or not, but just be sure you read the problem. I know it sounds trivial, like of course I'm going to read the problem, but it's easy in your haste, feeling the stress of the test, to just gloss over it and skim it and not really see what it is I'm asking for, and only give me what I'm asking for. It's also important to show me your work. I know that it's not going to be as neat as your homework. It needs to be legible nonetheless, but you need to show me everything you're doing. And it's in your best interest too, because if you don't get the answer correct and you don't show me your work, I can't give you partial credit. So it's important to show me a systematic way of how you did the problem, how you approached the problem and solved it, including the governing equations and the equations as they are, not just equations with numbers in them. Okay, any questions on the format? All right, well, if you think of something, let me know. Okay, so next is the different topics that you'll see. So chapter 2, I usually don't have questions specific to chapter 2, because chapter 2 is really just getting you ready for the rest of the class. So you learned how to convert force scalars into force vectors. There were a few basic equilibrium problems, but those are very similar to what we saw in chapter 4. So the main thing is these are probably the 4 broad concepts that I'll pull from. So moment about a point or a line, force couple systems, equivalent couples, equivalent systems. And those were covered on the homework. And you'll you'll know generally if it's this type of problem because it'll ask you, you know, to find an equivalent. When you say, whenever you see the word equivalent, that's a chapter 3 term. So versus if I ask you to find the reaction, that's a chapter 4 term. So just read the problem and it should be clear what I'm asking. I did make a study guide, which in the past I would let students use during the test along with a sheet of notes when during live test. I'll show you that in a second. But it has on it actually, no, I'll show it in a second. It has on it kind of the recipe for doing these problems. And I think it's a good source. I would review it. It's posted on Canvas under in the modules talking about solutions in the modules under solutions. So I'll show you that too. All right. So these are basically a summary. So we know moments about a line, moments about a point. I've kind of harped on that. Remember that a moment about a line is always a scalar. All right. And this lambda vector is always the unit vector of the line. And R is never a unit vector and always goes to the force. And I know I've said this ad nauseum, but it's really is something I see repeated over and over again where this is mistaken. And it's a very simple thing. If you just write down a note and, you know, and staple it to your forehead and just say R always goes to the force. Lambda is always the unit vector of the line, and R is never a unit vector, then you shouldn't have any issues. The force couple systems, remember that you're moving a force to a new location, and then you have to add a moment to compensate for that. And that R again goes from the new point to the old point. And the answer always includes the force, which means that it's not enough just to put the moment that you created. You have to also include the force as part of the answer. The equivalent couples, that's just adding couples together. So you had the one homework assignment with the 2 couples. I could give you something with, say, 15 couples, and you could add those together. Just have one problem on the test with 20 couples that you have to add, and then that's it. That wouldn't be a very effective test, but that's an idea. But so again, it's the same as a force couple system in the sense is that you just don't have any forces. So obviously there's no force in the problem, because if you add all the forces in an equivalent couple system, they all go to 0. And then lastly, the equivalent systems. And that's where you had the multiple forces acting on a single surface. And we only did 2D in that. 3D gets a little more grisly. And I haven't really seen 3D in a basic statics class. So if there's a problem like that, it would be in 2D. So that's chapter 3. Any questions on what I just said? All right. Now, chapter 4 is probably more familiar with you, and you probably found that chapter 4 is a little more straightforward because just the topics. You have your in 2D, of course, you draw your free body diagram, show all your forces and reactions, and then you have your 3 equations: some of the forces in the X, some of the forces in the Y, some of the moments, all equal to 0. And then when you go to 3D, it gets a little more complicated. The best way to do that is to, again, identify your force vectors and usually pick the point with the most unknowns to take your moment about that. And if you have a point that has equal unknowns, pick one. So, but you may have noticed on the homework that the problems, there's a certain similarity in the way you approach them. And that's kind of unique to statics, I would say, that because when you get to C204 in dynamics, the breadth of problems is much greater. And so as a result, you end up with a lot of different ways to solve it, a lot of different types of problems. But I think statics, most of the problems are pretty similar. Or at least maybe that's just what I think after teaching it for too many years. So, okay, so that's chapter 4. All right. Now I just want to show you that. Let's show you the So this was the study guide I told you about. And here you have the different chapters. And this just is shows you the steps involved for doing the different problems. And so I wrote it out as a kind of a list. And it might have been even part of the learning objectives that I've posted that I wrote for the class. But the idea is that you just, if you follow these steps, you should be okay. All right. Yeah, should be the latest version. So this is posted on, if you go into Canvas and you go into right here under assignment, quiz, exam solutions. There's the first 3 homework solutions, 3 quiz solutions, and how they go. Wallaby. Wow, that is strange. I wonder if I didn't save it when I did. No, I did save it. That is really strange why it's not there. I remember putting it up last night. Well, anyway, maybe I was having a senior moment, but I will make sure that thing is posted. It was right below here. I must not have saved it after I put it up. But again, these are past midterms if you haven't seen them. Winter, fall, all the way back. So this will give you a sense of the types of problems that you'll have. And I think I've already kind of shown you this, but just take a look at it. It gives you a level of difficulty and what you need to cover. Okay, so that's the test. So what are your questions? That's, like, as I mentioned last week, that's what this was about. If you had specific questions about anything that we will cover on the exam, now's the time to ask them.
I had a quick question about, I guess, a homework problem on homework 3. And kind of like approaching, I guess, when they draw in where moments are.
When you say where moments are.
Oh, sorry. I guess in number 4 on homework 3, they basically, saying, oh, use the relationship, like find a moment on this block. And then they have, of course, a bunch of forces, but also they have, half circles on point F and H saying like what the moments are at those locations. And I guess my question was, when you have when they draw in where a moment is, can you translate the moment across an axis?
Generally, a moment's a free moment. Let me look at that problem though, because I don't know that off the top of my head.
You said no worries. Yeah.
Homework number 3, homework 3, problem 4. You said?
Oh yes, yeah.
Okay, yeah. Let me just pull that up. So yeah, so in that one, the fact that the 42 and the 40 Newton meters are at F and H, when you add the moments in that, you notice that when you sum the moments about G, you don't have a distance attached to those. They just added in as 42 Newton meters, and they're both and 40 because they're both counterclockwise, so they're positive.
Okay, so you just add them to get 82. So I guess if you have a moment, or I guess let's say the 42 wasn't there, or just focusing on the 40 Newton meters, I can just translate that moment across the axis GH, right? Is that what it's kind of saying?
And are you talking about the moment or the force? I'm sorry.
The moment, 40 Newton meters.
Well, if you're saying the 40 Newton meters acts about G, it acts about H, it acts about any point on the whole object.
Okay.
So remember, they're free, so they just act on the entire body equally. So it's just think of them as something that's trying to make the entire body twist. So they're not bound to any particular point, unlike a force.
Okay, interesting. Okay, so yeah, if you have a moment, then that makes sense. It's just
It's just free. Yeah.
You can basically put it anywhere.
You can, yeah. And I mean, really, if you think about the math when you're using it, when you have a moment in there, if you sum moments up, it's just a number you put in the equation. There's no distance associated with it, right?
Sure.
Because the units otherwise wouldn't work out. If you multiplied it by a distance, you'd get Newton meters squared, which wouldn't. I don't know of a unit Newton meter squared. Wouldn't work. It's not newtons per meter squared, but Newton meter squared was what it would be. So yeah, it would work.
Okay, sounds good. And they just basically placed it around point H and point F for readability, almost.
I think so. Yeah, just so that they're there. You're right. So they could have put it at D. They could have put it at E. They could have put it in the center, as long as it's on the object. So you won't see a moment applied outside the object because it has to be physically onto the object. So
Of course, yeah.
just like a force that can travel infinitely, the moment doesn't really, I mean, it's associated to the boundary of the object.
Okay, awesome.
All right.
Thank you for clarifying all that.
Sure. Any other questions you guys have on anything? You can, let's see, I could do my shtick. In class, I would have a overhead projector and then I could make shadow puppets. The only thing is I can only do a dog, so it isn't very exciting. I sit there and go, woo, woo, woo. So I know it's too early for that, but
I had a question about moments about a line.
uh-huh.
I was wondering because obviously that equation where we use the dot product of the unit vector of the line with the r cross f. When we do that, we get a scalar. I'm just not quite sure if you needed that moment in vector form, say to add it to another moment or something like that. How would we get it in vector form? Would we dot it with, or would we cross it with the unit vector of the line or something like that? I'm just not sure.
Oh, I see what you're saying. Is what you would do is, let me see if let me put you guys on the others. Sorry, just getting it. There we go. So what you're thinking of is, yeah, how would you get into a vector? So what you would do is you'd have your r cross f. So let's say it's this line here, AB. So you have your lambda AB, you do your r cross f, there's your r, and then there's your force F. So let's say then you do that and it comes out to be a scalar, right? Because you're doing the dot. So you end up with, say, 60 Newton meters, and that's your scalar value. If you then wanted to get it into a vector, then you would do 60 Newton meters, and you could then multiply it by that unit vector. So you'd basically have, so what it would end up being, it'd be the moment AB would equal the scalar AB times lambda AB. Actually, sorry, that's the scalar. Just like that. And so you just, all it would do then is it would take the magnitude of the rotation about this line caused by this force, and it would put it into a form of a line. So then you'd get your IJK. And so it would just, it basically would just break it down the same as the unit vector. So the directions of each respective value would just be in the same direction as the IJKs of the line.
That makes sense. Thank you.
Sure. So you wouldn't, the only time you'd have to do this is if I specifically asked you that, but I generally don't. So this would be in a case as if I asked you to find the final moment about a line in vector form. So the way the problem's written really tells you everything. It would say, find the value of the moment about AB, and then you'd find it, and that would be a scalar. And if the wording specifically said vector, then you would do this. But this, I don't really usually do this, just because I don't know if that extra step helps. In terms of the real world application, that is a good question. I'm not sure. I think a lot of this in chapter 3 is just kind of getting you ready for other applications of stuff that's more important later on. I can say, though, that the ability to move a force somewhere else on an object is actually valuable. So if you have, physical object and you have forces acting, a force applied here, it may be such that this area of this component might be sensitive. It might be something that either the material isn't very strong, or there might be something near it that doesn't appreciate having a force applied to it. And in that case, moving the force somewhere else and then adding the moment can help it, because perhaps this area here is more robust. So I usually look at these things from my background as a metallurgist. I look at it more in terms of, how does the material handle these different things? Because if you apply too much force in an area, you can end up with overload failure, fatigue failure, fracture, all kinds of nasty stuff that ends up costing people lots of money or death. Okay, anyway, we diverge. What else?
Speaking of moving a force, I was wondering, with force couple systems, when we move a force using by adding a moment, I know we include the force in the answer, but I just can't remember do we include the original force that we were given, or do we include the force that is associated with the moment that we use to replace the force?
It's actually the same thing. So if you think about, depending on the complexity of the problem, but if you have something where, I think we did an example where it looked kind of like this, it was like a square object, and there was something down here. I think this was A and this was B, or this is B, and you had a force going down like that. And the question is, what if you move this force down here? And so when you do that, when you make an equivalent force couple at A, then really what you're doing is you're taking this force and moving it here, and it's the same force. So it never changes.
Okay, that makes sense. Thank you.
Sure.
Professor, I had a question on homework 4 problems is, so when do you assume that there's a moment about a point? Because I kind of noticed in the beginning ones, you're assuming some points can't support a moment. And then later on in the problems, you have to assume that it can support a moment. Is there a hint or a keyword besides it directly stating that it can or cannot?
Well, the ability, there's two things. Taking a moment about a point and supporting a moment are two different things. You can take a moment about any point, anytime, doesn't matter what it is, because that's not applying anything. That's just saying that about that point in space, everything has to be in equilibrium. So I think what you're asking, though, is how do you know what can support? And that's where you have to go back to the diagram in your book that shows you the different types of reactions. So, right, you have, if you have a pole in the ground, like I showed in class, then that can support, a moment about each direction and a force in each direction. Whereas if you have something like this, where it's, a ball and socket joint that's connected like that, then it can only support a force, but no moment. So it depends on the actual reaction type and how it's connected. So you can, you could picture if you have a beam that's cantilevered out of a wall, then it can support a moment. If it's a beam that's pinned to the wall, then it can't. So that's what you want to recognize the type of reaction. Generally, the reactions I give you on exams will be very clear because I don't want that ambiguity. I like to use ball and sockets or something like this. And if I think it'll be ambiguous, I'll usually say what can support and what can. But I would look at, I think it's page 173 in your book, has a list of reaction types. I think it's that page. And then there's also another set of reactions that I give out on the final that I'll also post for this. And it's a better set of reactions. It might even be online. It might even be still up there, but I'll make sure it's posted with the exam. And I got that out of a different book, and it shows different reaction types.
For the first drawing you did, is that like three different? Can it support three different moments, or one moment in the IJK components? And you had the three.
Well, it can support. I mean, it can support a moment about each axis. So I guess in theory, if you were to write the moment about that, it would be an IJK because each of these are different directions. Does that make sense?
Yeah, I was overthinking it.
Yeah. Yeah, don't overthink chapter 4. Just try to look at it straightforward. You know, make sure you set stuff equal to 0, narrow down. I won't give you anything where there's more unknowns than you can solve. And you'll always be a real question that has a real answer, not something that's. I'm not going to give you something that it's not doesn't exist in our universe. What else? Again, I can do the not very effective on this, so or we could play. You guys pick O.
I had a question about force couple systems. So I guess kind of like the examples are, do you pretend, I guess, that, well, even though like there might be two equal and opposite forces, when you solve, do you pretend that like maybe one of the forces does not really exist? To basically make it a problem.
When I think I know what you're saying that the fact that you have a force here, you have a force there, and then something like that. I guess it's not that it really exists. It's just that you're looking at the distance between them. So for example, on the homework problem, that what you found is if you go, say like this is your force here and you start at this point, if you go from this point to this point over here, then if that say goes down and across, like on the test, or I'm sorry, on the homework, remember this was, I think, 400 and this is a 30-degree angle. So this went, I believe this was 200, of course, and this was something like 364 or something like that. So if you go from here to here, then you essentially are going to follow the IJK components to get to this point. Once you get to the point, that's the force that you use in your cross product. So if that force is pointing, in this case, in the negative I, then you're going to use it in the negative I. If you went the other direction, if I went this way and that, then of course the R vector is going to have opposite signs because I'm going, in the Y and the positive Z, negative Y, positive Z. But when I get here, my force is in the positive X. So it really doesn't matter which way you go if you start here and go there. So I guess you're right. One of them kind of doesn't exist because if you're looking at the distance from here to here, you're starting at this point, since the force goes right through the point you're starting at, it doesn't have any moment because the distance is 0.
Okay, interesting.
What other deep questions do you have? All right.
Oh, I had a quick question.
Uh-huh.
I think this was based off quiz 2, but when I asked for the sum of moments about a point or a line, you can either do multiple, like I think the where it's this unit vector, it's dotted with the cross product. You can add multiples of that, or you can sum the forces first and then do the cross product of that times the scalar. Like either or, like they both work, right?
I think I follow your question. If all the vectors emanate from the same point, then you can add them together. If they're from different points, you can't.
I see.
So if you have an object if you have an object like I mean, so kind of like on the quiz, right? You had something like this, and you had a force here and a force there.
I think so, yeah.
You can't add those because if you're trying to like say find a moment about a line like this, then the r vector to here and the r vector there are different. Now, if both forces were like this and like that, then you could add all three and have a single r vector. But the fact that they're different, you have to, because then you're basically adding and multiplying together, and that violates the order operation. So you can't do that. So what I would say is just treat it as an individual unless the vectors have a common point on the object.
In that case, you would just do the scalar value dotted with the r cross f for each of them, right? If it was a moment about a line.
Yes, that's correct. The scalar value of the line dotted with, r cross f for each one. I mean, that would work on this too. It just, if you had 3 vectors here, you could do scalar r cross f, r cross f, r cross f. But if they're all in the same point, it makes more, it's less time consuming and less prone to error if you add them all together first and then do one r cross f to it.
Okay, yeah, that makes sense. Yeah, I was assuming they were in different points. That's why I was confused.
Yeah, if they're different points, then you definitely have to use a different r vector, and then you have to treat them as separate.
Okay, thank you.
All right. Anything else? All right. Okay, well, I will be in office hours from 10 to 12 if you guys think of anything. And if anything else comes up between now and the test, I'll definitely post it. But otherwise, look for the exam to be posted and available as of 8 o'clock on Wednesday morning. All right, you guys, thanks for coming, and I'll see you in office hours if necessary. Good luck.
Thank you.
You also have
Thank you,
office hours
Professor.
on Tuesday, right?
I do, yeah. I have office hours today, and then again 1 to 3 on Tuesday also. So either one will help.
All right, awesome. Yeah, see you then, and
All right.
have a good rest of your day.
Thank you. You too. Bye-bye.
Thank you.
Bye-bye.
Thank you.
Thanks.